Hello, my name is Simwa Bright Samuel, and me and my group mates we're going to be taking you through the presentation for our final year project. So, I'm present. Sorry, the title of our final year project is Modeling and Control of Mixed Traffic in Developing Cities Using Reinforced Learning, and I'm going to be going through the introduction. So, my group mates are Moise Gwajodan, Kaiwa Joshua Bim, and Saka Morris Baraka. So this is the project outline from the background. I'm going to take us through the background, the problem statement, and the objectives. So starting off, so why traditional models fail in Kampala? So this is the problem, the background to the problem we are going to be addressing. The models fail due to a major assumption of lane-based traffic flow that breaks down in mixed traffic. So we have a lot of motorcycles in our traffic. Like most of the our traffic is comprised of motorcycles, and this traffic is rather mixed. And you find that these motorcycles they do not follow the roads, the traffic lights, and the traffic is actually quite a lot in most cases. So with border borders being a major contributor, they make up the largest share of vehicles in Kampala, and the traffic lights that we have, they have fixed time lengths, sorry, fixed time signals and signal timings that do not change with demand. So um, we are proposing simulation of urban mobility and adaptive approaches like reinforced learning, provide an opportunity to model and control such complex traffic environments more effective. Okay, moving on to the next slide. So the problem statement is we don't have an adaptive traffic signal control approach for heterogeneous, the mixed traffic that we have in Kampala. But we do have the models available to control the traffic, though for the mixed traffic, we do not have that. So in our problem statement, the traffic signals in Kampala, they mostly use fixed time control in that they calculate the time for showing the red or green, then the fixed time signals they do not adapt to the changing traffic demand. Then also we have the vehicle behavior, it's very unpredictable. The existing reinforced learning traffic control models, they assume lane-based traffic. The performance is mixed. Then there is no validated reinforced learning signal control currently in Kampala. So the current traffic lights, they do not respond to real-time traffic and leads to wasted time, fuel consumption, increased frustration for road users. The current traffic lights do not, okay, remember we are generally talking about the mixed traffic, yeah? So looking at that looking in that perspective, yeah, it's the problem we're trying to address with the reinforced learning technique. Sorry, the reinforced learning proposal. Continue. So the main objective for this project is to model and control mixed traffic in our developing city. The mixed traffic that is full of many motorcycles that usually do not even follow the road, whatever is the road signs, sorry, the road traffic lights because the traffic lights they're just based on time. They do not cater for, let me say, if a road is empty and it's not being, and this side the road is full of traffic, yet people are just there waiting. So to model and control mixed traffic in a developing city context using reinforced learning and simulation of urban mobility based simulation to improve traffic signal performance at an urban inspection intersection, sorry. So the specific objectives are to model and calibrate the sumo-based simulation environment and to implement reinforced learning traffic signal control algorithms to compare the performance so that can come up with um something to, okay, I would say the reason for comparing the performance of reinforced learning controllers against fixed time control using it's to come up with a solution for the fixed time control using the indicators such as delay, how long cars wait, then the queue length, how many cars wait in a lane, like traffic lining up in a certain lane, then the throughput, how many cars pass in a certain junction, then the emissions. If there is a heavy emission, the traffic is a lot. That means many vehicles are waiting in the traffic in the intersection. Then if it's low, that means the traffic is low. Then to evaluate the effectiveness and limitations of reinforced learning in managing mixed traffic in developing city environments. Thank you so much. The next presenter will take us through the next part.
Good afternoon. My name is Barack Morris, and I'll be taking you through the literature review of our project. So now, the things we investigated about regarding the project, first of all, was, of course, reinforcement. I beg your pardon. Reinforcement learning for traffic signal control. So reinforcement learning is an AI-like method of learning that enables adaptive signal control based on real-time traffic conditions, and it outperforms fixed time control. Now, fixed time control is, of course, the traffic lights having simple 5-minute, 2-minute intervals between the red and green lights to allow the cars from different lanes to merge and to stop. Then it also outperforms fluctuated control, and this has showed significant improvements in the metrics of traffic, which would be the reduced average delay, the shorter queues, and the improved throughput. The average delay is, of course, how long it takes for the cars to finish, for the cars to move without getting stuck in traffic. And several studies showed that reinforcement learning is highly effective for this adaptive traffic signal control. And the major surveys which we have put in the supporting studies can back that. So now these systems have reduced the vehicle delay, the queue lengths, and the travel time by learning optimal signal timing and directly from the traffic conditions rather than relying on predefined schedules. So now this will show that once there's a buildup of traffic in one lane, then the system will adapt to that buildup and try and ease the traffic by slowing the traffic down where there's less congestion, and actually letting the more congested parts of the traffic to move through. So why Sumo? Sumo, of course, is an open source simulation platform, and that's what we're looking for in regards to our project, something that will be less costly and still effective. And it also supports the mixed vehicle types, which we aimed to achieve to model, which will be the cars, the taxis, the boarders, all those. We're planning to have those incorporated in our models so that we can have a more local, a more customized project that will cater for Uganda and for Kampala. Then real-time control via TRLCL. Now TRLCL is an interface that helps us control the traffic, and further integration with reinforcement learning agents is another thing that we'll have to achieve while using Sumo. In addition, the microscopic simulation enables vehicle-level behavior modeling and safe evaluation of control strategies. Now, vehicle-level behavior modeling, for us in particular, this can cater for the taxis and the boarders that have no regard for traffic rules. So now, so that will be incorporated, and that's it's a major bonus for us as a country. And for this project, since it will work more effectively for Kampala. I'm going to put that slide. So now, why reinforcement learning theory? Reinforcement learning theory is grounded in the concepts of Markov decision process, value functions, policy, optimization. Yes, so now Sutton and Bartol's work provides the core framework for the breakthroughs in such deep Q learning networks and high dimensional, to operate in high dimensional environments like traffic systems. And these foundations will underpin the modern RL, reinforcement learning based traffic signal controllers such as PressLight and IntelliLight, which we'll be using. Next slide. I think my colleague will highlight on the identified research gaps in this project.
Hello, my name is Kaiwa Jashabir, and I'll be taking us through the identified research gaps from the literature review. So first, we discovered there was a lack of reinforcement learning studies for non-lane-based traffic, as most studies assumed structured lane discipline. And secondly, we also discovered that there was a limited application to developing cities. African urban traffic was largely unrepresented by most of the models that were developed. And so that kind of model that has been developed for a more developed country would be like not feasible with Ugandan context or African context with mixed traffic. And we also discovered there was unrealistic sensing assumptions. So most of these models rely on developed infrastructure like cameras, sensors, but such things are not really available in Uganda. And so we'll have to work with limited data intake. And so, yeah, that was another gap that we realized. And finally, we also discovered there were few evaluations under extreme congestion. So peak hour conditions in cities like Kampala are rarely modeled. They usually model moderate kind of situations. And yet the usual situation in Uganda is packed lanes. So yeah, those were the research gaps, and we'll now go into the research methodology. So our first action in the research methodology was, will be collection of real world data. Then next we shall do the data processing. And then after that, we shall create a simulation from Sumo. And then we shall do the reinforcement learning environment and model development. And finally, we shall do the evaluation of the models that we have developed. Just below there, we see an example of a simulation that has been created using Sumo. My friend Jordan will take us through a deep dive of the research methodology.
Hello, and I'm going to take you through the research methodology. So first we have the data set and data collection, how we collected our data. We used the KCCA reports, UNA Array transport statistics, Google Map traffic data, OpenStreetMap, road network. So for data cleaning and preprocessing, we normalize the traffic counts, we derive the traffic demand matrices, prepare the heterogeneous vehicle definitions, and prepared the RL compatible traffic states. For data exploration, there's congestion pattern analysis, simulation-based traffic visualization, RL state space diagnostics. And for system implementations, as my colleague said, the Sumo, we opted for the Sumo simulation environment. Then we use the RL algorithm design, and
the RL environment implementation. For evaluation, we did performance metrics, experimental design, and statistical analysis. So our work plan, as you can see, this is how we carried out for each activity. The requirement analysis first week, then it took us a week. And then weeks 3 to 4, we did data acquisition. Then the data cleaning was done in 5 to 6. Then the Sumo network setup, as you can see, it was also done the following week, 7 to 8, and so on, as you can clearly see in the work plan. Our budget was as follows. Our budget for the project is as follows. The internet, which will be used for downloading datasets, running the simulation, that was a budget 200,000, which totaled up to 800,000. Then printing and binding, the proposal and the final report. Then the unexpected expenses, of course, which all came up to a total estimated cost of 900,000. Yeah, that's it for our presentation. Thank you.